Hello everyone, my name is Harry Anthony and welcome to my presentation for Unsure 2024. Consider the setting I'm training a deep neural network for medical image classification, such as diagnosing skin lesion images, with a set of images and corresponding labels which makes up my training data. Once a model is trained, it can be applied to unseen images from the same distribution as the training data, which we call in distribution. But what happens when it's applied to an image which is significantly different from the training data, which we call out of distribution, or OD? Well, what we see is diagnoses on OD data are both unpredictable and unreliable. This motivates the field of out-of-distribution detection, which aims to detect when an input is from a different distribution from the training data. Out-of-distribution detection methods typically give a scoring function for each input image. To quantify the ability of the scoring function to separate ID from OD images, we typically use the area under the ROC curve, or AROC metric, which is threshold independent, where the true label is ID and the false label is OD. However, there is a growing body of research which is arguing that out-of-distribution detection framework does not effectively reveal which method is best at detecting errors. They propose evaluating methods on their ability to discard incorrect predictions, regardless of whether these predictions are from OD inputs. As with OD detection, for failure detection methods, we get a scoring function for each image. We typically quantify the performance of failure detection using AROC again, but in this case, the true label is if the diagnosis is correct, and the false label is an incorrect diagnosis. In this paper, we studied post-hoc OD methods, which are methods which use the features and outputs of my pre-trained model for my ID task, rather than making an external model solely for OD detection. For this paper, we group OD detection methods into two groups. The first group, which I will call confidence-based methods, use the output layer of the network for OD detection. For this study, we analyzed 12 confidence-based methods listed here. Some of these methods have hyperparameters that can be optimized on an external validation set. The other group of methods are feature-based methods, which don't use the model's output layer, but instead use the model's hidden layer data for OD detection. Our analysis was completed on two medical datasets. The first is D7P, which is a dermatology dataset. To create an OD benchmark, we manually annotated this dataset into two subsets, images with no rulers and images with grid rulers, with the latter being our OD test cases. The model was then trained on 90% of images with no rulers to classify between images with nevus and images without nevus. Once the model was trained, the OD methods were applied to see if they could separate the held out ID images from the OD images. The next dataset analyzed was BreastMNIST, where we separated images without annotations from images with annotations, with the latter being our OD test cases. The model was then trained on images with no annotations to classify between malignant tumors, benign tumors, and images with no tumors. And then the OD methods were applied to the held out images. Let's look at the results. On the x-axis, we have our outer distribution AROC, and on the y-axis, we have our failure detection AROC. We're starting with a BreastNet 18 model trained for the BreastMNIST task, where we're showing the mean of 5 seeds. So let's place our confidence-based methods, then our confidence-based methods which have an optimized hyperparameter, and then finally our feature-based methods in green. What we see in general is the confidence-based methods perform better than the feature-based methods at failure detection, whereas the feature-based methods perform better than the confidence-based methods at OD detection. We see this again for BreastMNIST with the VGG16 model, as well as for our D7P task with the ResNet 18 model, and our D7P task with a VGG16 model. To analyze this further, we created a counterfactual dataset by synthetically removing the OD artifact from each of our OD images. This was done using intra-image interpolation, where we replaced the artifact with another patch from the same image. For more details on how this dataset was made, please visit my GitHub repository. We studied if the model diagnosis was correct with the artifact and without the artifact using our synthetic images. We then used this to classify all of our OD images into 4 groups, depending on if the model diagnosis changed. Here are the distributions of predictions for the whole of the BreastMNIST dataset, where the pie chart shows our 4 categories of predictions discussed before. We can then study what happens when we apply different OD detection methods. We study the performance of a confidence-based method, maximum class probability, and a feature-based method, Mahalanobis score. For our analysis, we first calculate the scoring function for each image using our OD method. We then calculated the 75th percentile of the scoring function for the ID test cases, and removed all diagnoses below this threshold for both OD and ID data. Here are the diagnoses above the threshold for MCP. What we see is the accuracy of the diagnoses for both ID and OD data has increased, but the percentage of OD images past the threshold remains high, and the percentage of images which are correct only with the artifact has actually increased. As for Mahalanobis score, Although the percentage of remaining OD images above the threshold is lower, the accuracy for both ID and OD data actually decreases, and so the method succeeds where the confidence-based method fails. These results motivate integrating both a confidence and feature-based method into a pipeline to compensate for their respective weaknesses. To study this, we applied MCP on top of the predictions passing the Mahalanobis score threshold. What we see is the remaining predictions are both more accurate, and the percentage of OD images above the threshold remains low. Although it results in more predictions being dismissed, we argue that this configuration leads to a more reliable DNN predictions. So, to conclude, outer distribution detection is not the same as failure detection. We saw that confidence-based methods typically outperform feature-based methods at failure detection, whereas they perform worse at OD detection. And finally, we suggested combining a confidence-based method and a feature-based method in a pipeline can mitigate against their respective weaknesses.